Really brief video here because I found the example that I was trying to bring up when I did that cosine squared thing. This is what I actually wanted to do. I wanted to do this example for you of integration by parts, where we do the integral of e to the x sine x dx. Same kind of trick that we're going to do here is going to work if that's a cosine too. This is the example. Okay, I'm glad that I figured that out because it was driving me nuts why the example I was doing was not doing what I wanted it to. And this is why. So this is what I wanted to do. What I'm going to do here is not a lot of choices here. Both choices work out kind of the same way. I'm going to take u to be equal to sine x, then du is cos x dx. dv has to be e to the x dx, and then v is equal to e to the x. Okay, well, that's not great, but whatever. uv is then going to be e to the x sine x, and then we're going to be subtracting off of that the integral of v du. So that's going to be e to the x cos x dx. And so that's okay so far, except it's not really any better than what we've got at the start, right? I've just interchanged a sine and a cosine. Seems like we're getting nowhere quickly, but taking a long time to do it. However, if we repeat this procedure, something really cool happens. So what I'm going to do is I'm going to say, okay, let's take u1 to be equal to cosine x. That makes du1 to be minus sine x dx. That makes dv1 is going to have to be e to the x dx, and then v1 is still going to be just e to the x. So this becomes e to the x sine x minus the integral of. Now, this is where we got to be careful because we're going to have minus signs floating around all over the place, and if we're not careful, we're going to end up with something wrong because we're going to have the wrong sign. So we are subtracting u times v, that is e to the x cosine x, minus, sorry, that's not an integral, minus uv and u1 v1 minus the integral of v1 du1, which is negative e to the x sine x dx. There we go. Okay, now this, and I'm going to write it up here for reasons that are going to become clear in a moment, comes out to be e to the x sine x minus e to the x cosine x plus the integral of e to the x sine x dx. Okay, seems like, once again, we're just spinning in circles. And we are spinning in circles, but that's actually okay in this case. It's really okay that we're going about in a circle. Because here's what has happened. What we have actually done here is we have an integral of e to the x sine x dx plus a bunch of stuff plus another, wait, did I lose another minus sign? Yes, I did. I'm sorry. This should be a minus here because I have 1, 2, 3 minus signs. That should be a minus sign. Because now what I can do is I can say, take this whole chain of inequalities that I've conveniently written so our first thing and our last thing are next to each other. I can move this integral over to the left-hand side and watch what neat little thing happens. I'm going to throw in a plus a constant of integration over here just because we need one for completeness for the next step. This tells me that 2 times the integral of e to the x sine x dx is equal to e to the x times sine x minus cosine x. So notice what has happened here is even though we did integration by parts twice, we still ended up with our original integral coming back. But that's okay because I can move that integral to the other side and solve for it, and I get the integral of e to the x, oh, and I forgot my constant here, the integral of e to the x sine x dx is equal to 1/2 e to the x times sine x minus cosine x plus our constant of integration. And even though the constant got multiplied by 1/2, we're going to not worry about that because a constant times 1/2 is still just a constant. So what we've done here is we have iterated the integration by parts. And what's happened is we've ended up back with the same integral we started, but then we can just solve for that integral. So you could do the same thing if you had started with, say, the integral of e to the x cosine x. Same kind of pattern would happen. So this is a very convenient and very neat thing because in some sense, we've found the integral without ever actually doing the integral. We've done other integrals as part of our integration by parts stuff, but we never actually had to do this integral. We just had to do some related integrals, and it kind of fell into our laps from algebra. Okay, so that was the example I meant to do when I did the cosine squared. Now, do not worry, we are coming back to the cosine squared example because that is an important one, and we do want to know how to do it, and it is perfectly feasible to do it. But yeah, it wasn't the example I was looking for. So we're going to come back to that as we start talking about integrating trig functions in general. All right, I will let you guys go at that point, and that kind of takes care of pretty much everything I want to say about integration by parts. Like I said, there's more examples that you want to think about. And of course, I should mention also, integration by parts, you can do it using definite integrals as well. The only change is that if you're doing the integral from a to b of u dv, well, this is uv evaluated from x equals a up to x equals b minus the integral from x equals a to b of v du. Okay, so you can do the definite integral just by using the fundamental theorem of calculus together with your standard integration by parts stuff. There's not really anything new coming in there. So be sure that you take a look at some examples of that, but it's really not anything, hopefully, different than what you've been doing before. All right, so there we're actually done with our integration by parts stuff for now. We will continue to use this technique, though, as we talk about how to integrate trig functions and things. We'll be talking about using substitutions and integration by parts, and we're going to be talking about using trig identities, all kinds of stuff for that. Anyway, for now, though, I am going to stop here.